So my dear students, my name is Vigyan Tiwari, working as assistant professor at SITS Bhopal. So today we are going to see this minimization of finite automata. So there is a question arises that why we'll have to minimize the finite automata. So for that, stay tuned. I will let you know shortly why we require this minimization of finite automata. So before we see this procedure, that is minimization of finite automata, we'll discuss why we required that to minimize that finite automata. So first of all, we know that how to implement that DFA. So for each state, we write a method while implementing the DFA. So if we have lesser number of states, we have lesser space complexity and we have lesser time complexity. So that is how we are, why we are minimizing this finite automata. So this is the requirement of this minimization. Okay, now let's see the procedure. So we have this, if we have a FA, so we have number of state is there. So if we have the number of state, what we'll do, what we can do, so we'll have, so we have, let us suppose, so we have states, okay, because we have finite automata, okay. So assume these transitions is there, okay. So we'll have to minimize this state, okay. So we have number of states available and that is known as Q. We know this one. This is Q and we have 3 states right now. Okay, we have 3 states given here. So name it just Q0, Q1 and Q2. So we have 3 states and we'll have to minimize this one. Okay. So what will happen? We'll have to minimize this Q. So that is how we are going to make this pi k equivalent. Pi k means in each state we'll have to identify the equivalence classes. Okay, so we'll have pi 0, we have pi 1 and pi 2. We'll see how we are going to calculate this pi 0 and pi 1. So whatever with the states present there in this pi 0, so the states should be equivalence. So for a single input they'll have to go to the same state. So that's why they are that k equivalent. Okay, so let's suppose that we are going to construct pi 0. So we have 2 states there. Okay, so in this state, so we have 2 parts basically. In this part, what we have final state is there, and in this part, what we have non-final states there. So we categorize the states in 2 parts. The first part contains what? Final states, and the second part contains non-final state. That is written here itself. You can see here. So final state belongs to Q1 0. So these are 0 equivalence classes because the nature of the states in this Q1 0 is similar in nature, and that's why it is known as equivalence classes method. So equivalence in what terms? In terms they have the same nature for a single kind of input. Okay, so this is how we are going to make this pi 0. Okay, now from pi 0 we can construct pi k plus 1. So pi k plus 1 means, so we have pi 0 and we'll do plus 1 in this itself. So we are going to get what? Pi 1. So if this is k, then we'll have k plus 1, that is pi 1. Okay, so k equal to 0 right now. Okay, so see, so pi 1 is always constructed by using pi 0. So pi 2 is always constructed by using pi 1 itself. Okay, so that is the meaning of pi k plus 1 from pi k. Okay, so while making this pi 2 from pi 1, what we consider only one thing, that from a state for a single kind of input, if we have the same transition, then these 2 states belong to the same equivalence classes. Q1, by seeing A, it goes to the same state, while At the same time, Q2 by seeing A is also going to be a same state. So what we'll have to do? So it means these both state belongs to the same class. Same class. Whatever be the class, so they are going to belong to the same class itself. Okay. If they have different states, it means they are in different class. It means they are in separate classes. Okay, they are in separate classes. So that is how it is written here. Okay, so for a state, in a state, for a single input, we'll have to check the transition. Okay, then we can say they are equivalent in nature. Okay, so when we'll have to construct this pi 1 and pi 2 till pi n. So if two equivalent classes are in same in nature, that is pi n and pi n plus 1, here we'll have to stop our construction of pi k equivalent. Here we'll have to stop our construction while pi n and pi n plus 1 are in same nature. Okay, from there we can say that we successfully minimized our finite. Now we are not able to minimize further after seeing this pi n and pi n plus 1 if they are equivalent. Okay, and at last we'll have to do whatever the state we have took together, we'll have to make it in square bracket itself. So now we'll try to implement this procedure soon. Okay, we'll see the procedure what we are going to do right now. So let's try to implement the procedure here. So we have a finite automata given here. So I have made here transition table for that one. Now let's see. So we'll have to construct this pi 0. So we know in pi 0 we have two parts. The first part contains the final state and the second part contains the non-final state. So this is the final state, it is clearly visible here, and these are the non-final states. Okay, so I have written here. So now we'll have to construct pi 1 from pi 0 itself, and that is what is written in procedure 2. That what we'll have to do, pi 1 will be constructed by using this pi 0. Okay, let's see it. So do one thing, make this part 1 and make this part as a 2. Just named them. Okay. Now see from here what is the transition. So it means for Q0 we are reaching towards Q1 and Q5. So make a set here itself. So for Q0, see here in transition table for Q0 we have Q1 and Q5. So Q1 and Q5 belongs to here itself. So we'll write 2, 2. 2, 2. Just write 2, 2 here itself. Okay. So for Q1 we have Q6 and Q2. Again find here Q6 and Q2. So what we have 2, 1. Just give a name. So they are in equivalent nature. We need not to see this Q2. Q2 is already separated from this one. We have Q3. Again we have Q2 and Q6. Q2 and Q6, that is 1, 2. Q2 belongs to 1 and Q6 belongs to 2. Again we'll see Q4. Q4 is Q7 and Q5. So we have Q7 and Q5, that is 2, 2 again. So we have Q5, Q2 and Q6. It is clearly visible here, Q2 and Q6. So Q2 and Q6, again we have 1, 2. Q6 and Q4. Q6 and Q4, that is 2, 2. And last but not the least, we have Q7. That is Q6 and Q2. So we have this Q6 and Q2, that is 2, 1. Now see, which is having the similar nature. So by this way we are going to identify the similar nature of them. So 2, 2. So this one and this one this one. So this belongs to Q0, this belongs to Q4, and this belongs to Q6. So see, they are in the same class. Now see this 2-1. 2-1 is where? This is for Q1, we know this one, and we have this one, 2-1. That is Q1 and Q7, the last one. So you have, they are in equivalent classes, and the remaining is what? 1-2 and 1-2. That is Q3 and Q5. We have this one. So by this way, we are going to construct again pi2 till pi n plus 1 will remain the same. We will stop our construction there itself. So now see how we have constructed this pi2 by considering this pi1 itself. So what we'll have to do again, we'll have to write state here. So remember this one, pi2 is always going to be constructed by using this pi1 itself, not pi0. So we'll write 1 here, 2 here, 3 here, and 4 here. Now let's try to understand. We'll have to make the set of that one. Okay. Now again we'll see here. So for Q0 what will happen? Q1 and Q5. So we'll check here itself. Q1 and Q5. So sorry, here itself. So Q1 and Q5. So what we have? 3, 4. Again for Q1, Q6 and Q2, Q6 and Q2, that is 2, 1. We have this one. Again for Q3 we have Q2 and Q6, Q2 and Q6, so we have 1, 2. Again what we have? Q4, and for Q4 what we have? Q7, Q5. Again we see Q7 and Q5, that is 3, 4. And Q5, Q2, Q6. So we have Q2 and Q6, 1, 2. And we have Q6, Q4, Q6, Q4. So Q6 and Q4, that is 2, 2. And for Q7 what we have? We have Q6, Q2. So here we'll have to check Q6 and Q2. So we have 2, 1. Now see the similarity between them. So this is for Q0, 3, 4, and we have there. So Q0, Q4 remains same. Q0 and Q4 will remain same. So again we have this is for Q1, 2, 1. 2, 1 is there, 2, 1. So Q1 and Q7 will remain same. Here we have, and we have 1, 2 here, and we have 1, 2 here. So this is what? Q3, and this is what? Q5. So Q3, Q5 will remain the same, but we are only left with this 2, 2, that is Q6. So Q6 will be this. So now by using same nature we are going to construct this pi3 until pi2, pi3 same, pi3, pi4 same. We'll stop there if they are in same in nature. So to construct this pi3, again we are going to follow same step. Pi3 will be get constructed by using pi2. We'll rename here 1. Sorry. We will rename here yet itself. So we have 1, we have 2, we have 3, we have 4, and what we have? We have 5 here itself. Good. So it is clearly visible here that pi2 and pi3 are in same in nature. So from there we can conclude that we'll have to stop our construction, and the pi2 will be the final result because pi2 and pi3 is same. Okay, here we'll have to stop our construction and see. Let me clear the screen first. So this is what we get in pi2. In pi2 we have this one. Okay. So now convert this curly braces into this square bracket. The square bracket means what? it is a single state. Remember this one. This is Q0, Q4. It means there are two states for a same transition, and in case of Q0, Q4, we have a single state. It means what? Let's try to understand. So Q0, Q4, two state. Okay, so let's try to understand. From a state, for a input, we reached to Q0. This is a state. And this is again for A, we have again a state here itself, that is Q4. If we are having this curly braces, and what about this one? About this one, it means for a single input, what we have? We have a single state is there. It is treated as Q0, Q4, a single state. It means this is a single state. So this is the difference between this and this one. So this will be treated as a single state. Okay. So it is clearly visible here. So these are the state. So Q0 initial state will become this Q0, Q4 because we don't have any Q0 state is there. So Q0, Q4 collectively known as a single state. Okay. So these all are a single state. So it is clearly visible. We have how many states we have? 1, 2, 3, 4, 5 states are there. And how many states we have earlier? 1, 2, 3, 4, 5, 6, 7, 8. So from 8 we get reduced to 5 state. So that is how we are going to minimize the state, and the final state is Q2 itself. It is clearly visible from here itself. So how to make this transition table? By seeing this one. So initially we have Q0, we know this one, and we right now we don't have a Q0 state. We have Q0, Q4 collectively known as a single state. That's why we have written Q0 and Q4 here. Okay, so see, by seeing this Q0, we reach to Q1 itself. Okay, so here we have Q1 and Q7. Why we have written this one? Because we don't have any state named Q1 itself. The state is Q1 and Q7, and that's why we have written Q and Q7. So see, by seeing Q0, we reach to Q5. So we don't have any Q5 state there. What is the name of a state? Q3 and Q5, and that's why they are same in nature. Okay, so by seeing this one, we are make this transition table. So hope you have understood this one. Similarly, you can go for this one. So remember this one only, that we don't have this is not treated as a single not treated as a two states. This will be treated as a single state itself. So that is how we are going to minimize this finite automata, and this is also known as equivalence classes method. Okay, so for a state, for a single input, they are having the same nature. Okay, so thanks for watching this one. Again, thank you, and stay tuned and keep learning.